Hello everyone, welcome to another ALEKS video. In this episode we are going to be finding a chemical formula or molecular formula from a mole ratio. So let's look at this problem. It says that this compound X has a molar mass of 283.89 grams per mole and has the following composition. So 43.64% of this compound is phosphorus and 56.36% is oxygen. Now, it might be tempting just to think that in this case, phosphorus just makes up 43.64% of the compound's mass, and oxygen makes up 56.36% of the mass. And while that is true, the mass percent is this. That is not the case for how many moles of each substance is in this compound. And the reason for that is that every element has a different molar mass. So this video is about showing you the trick to solving these problems. So the first thing you can do is you can take your mass percent and you can let this mass percent, for simplicity, let the mass percent be out of 100 grams of substance. And what this allows us to do is we can just directly say that this 43.64% represents 43.64 grams of phosphorus. And this one represents 56.36 grams of oxygen. Now what we can do is that we can use the molar mass of each element to find the number of moles. So, phosphorus, if we check the periodic table, phosphorus has a molar mass of 30.973762. So, that's according to ALEKS. So, and we're just going to use the ALEKS value. So, if we want to find the number of moles of a substance, we can put number of moles on top and cancel with grams. So, what that's going to look like is we can say that 43.64 grams of phosphorus is multiplied by the molar mass with grams on the bottom, so it cancels. So that would be 30.973762 grams of phosphorus per every 1 mole of phosphorus. The grams of phosphorus cancel, and we're left with 43.64 divided by 30.97 blah blah blah. If we do the calculation, we're going to get 1.4089 moles of phosphorus. Now we're going to do the same for oxygen. So we're going to take the grams of oxygen, 56.36 grams of oxygen, and multiply that by the molar mass with grams on the bottom. So this would be 15.9994 grams of oxygen over 1 mole of oxygen. The grams of oxygen cancel, and we are left with 56.36 divided by 15.9994. And that's going to give us 3.5226 moles of oxygen. Now, what we've done here is that we've converted this mass percent into something we can use for our chemical formula, because our chemical formula is made out of moles, right? For instance, H2O, water, consists of 2 moles of hydrogen and 1 mole of oxygen per every 1 mole of water, right? So we're dealing with moles here. So what we can do is that using this mole ratio, we can put the higher number, which is oxygen, on top of a fraction and the lower number on the bottom of the fraction, and we can see how many moles of oxygen we have per moles of phosphorus. So let's do that. Let's put the larger number on top, which is oxygen. This will be 3.5226 moles of oxygen for every 1.089 moles of phosphorus. And if we divide, we are left with 2.5. So what this means, if this equals 2.5, that means that for every 2.5 moles, for every 2.5 moles of oxygen, we have 1 phosphorus, 1 mole of phosphorus. Now, to make this a little clearer, let me rewrite this in fraction form. So, once again, if we divide 3.5226 moles of oxygen by 1.4089 moles of phosphorus, the simplified fraction is going to look like 1.2 moles oxygen over 1 mole phosphorus. So again, we're just simplifying this fraction, right? And that, the English translation of that would be, there are 2.5 moles of oxygen for every 1 mole of phosphorus. Now, of course, you can't have 2.5, you can't have a decimal amount of moles in an empirical formula. That would look ridiculous. I mean, think about it. You can't have H2O be, you can't have H2.50. That doesn't make any sense. So you have to deal with whole numbers only. You can't have decimals. So we can get around this by just multiplying by 2. We know if we multiply 2.5 by 2, we're going to get 5. But you got to remember to multiply both of them by 2. If you multiply both of them by 2, this expression just becomes, there will be 5 moles of oxygen for every, multiply it out, multiply this 2 over, for every 2 moles of phosphorus. So if there are 5 moles of oxygen for every 2 moles of phosphorus in this compound, logically, that means that our empirical formula is going to be P2O5. There are 5 moles of oxygen for every 2 moles of phosphorus. That's what this means. Right? Now, are we done? No, we are not done. We are not done because this is what we call the empirical formula. What that means is that an empirical formula is the simplest unit of this compound, right? So, this compound's going to be made up of this empirical unit, right? This empirical formula is this. However, we're not asked for the empirical formula. We are asked for the molecular formula of X, where X has a molar mass of 283.89 grams per mole. So how do we find that? Well, what we can do is we can find the molar mass of our empirical formula, which is P2O5. So if we find the molar mass, well, we already found the molar mass of our individual elements, right? The molar mass of phosphorus is 30.97 ... The molar mass of oxygen is 15.9994. So, all we got to do is do what we've already done a few times, hopefully, what we've already done before, and just find that the molar mass of P2O5 is going to be equal to, there are 2 phosphorus, so 2 times the molar mass of phosphorus plus there are 5 oxygen atoms, so 5 times the molar mass of oxygen. Plug that into your calculator and we get that the molar mass of this empirical formula, P2O5, is equal to 141.944. And that is grams per mole. So that is the molar mass of P2O5. Now all we have to do is divide the molar mass of our compound by the molar mass of the empirical formula. So if we take the molar mass here, if we take this down here, if we take this 283.89, and we divide it by the molar mass of our empirical formula, which was 141.944. What we are going to find if we plug this into the calculator is this comes out to 2.000000 and then some number over here. We don't care about this because it's so small. It's such a small decimal place that we can just call this 2. So what does that mean? It means that there are 2 P2O5 empirical formulas inside the chemical formula. Let me choose a different color here. So in our chemical formula, oh my goodness. In our chemical formula of X, we have 2 times what is our empirical formula. So, all we need to do is just multiply the 2 into our numbers here, and we're going to get that the chemical formula of X is equal to P4, 2 times 4, right? O10. And this is our answer. And remember, this is the chemical, also called molecular, formula of X. The empirical formula, P2O5, this is the empirical formula of X. So on your exam, make sure that you are careful and you're reading what the question asks for. If it asks for a molecular formula, then you have to divide the total molar mass of the chemical/molecular formula by the empirical formula to see how many units of empirical formula are in the chemical formula. And that's how you solve this problem. Hope you learned something, and I'll see you in the next video.